We present in this research recurrent transition networks for character locomotion. Our system takes as input a few frames of motion as past context and a desired target state as future context. It then learns to reconstruct the missing frames in order to generate realistic transitions. Recently proposed deep learning approaches for motion prediction fail on the task of transition generation as the target state cannot be precisely inferred from the past context alone. We now give an overview of the system on a single time step. Our model has three separate encoders that are multi-layered perceptrons. The frame encoder takes as input the current character positions with a local terrain representation. The future encoder takes as input the normalized target positions and velocities, while the global offset encoder processes the difference between the target positions and the current positions in global space. Their outputs are then combined in a modified long short-term memory layer that takes as additional input its own previous state. This is where the modeling of temporal dynamics and future context conditioning are done. This recurrent layer produces a representation that is processed by the frame decoder, which is another multi-layer perceptron. This decoder outputs positional offsets from the current pose in order to produce the next character pose. Here are some raw outputs from the RTN without any post-processing. We compare our method with quaternion spherical interpolation and two other deep learning approaches that we augment with our future awareness strategy. The ResNet LSTM struggles to produce realistic movements even though it performs well on short-term predictions, while the ERD network produces realistic movements but suffer from the known offset problem when going in and out of transitions. The RTN mitigates most of these problems but can still show minimal jumps only when coming out of the transition. Here are more results of our method with a target blend post-process that smooths out the end of transition error. We use the target information to smoothly correct the generated transitions. This can work only if the end pose is close enough to the target. Diverse locomotion and terrain traversal skills are successfully reproduced by the network. We also apply the RTN on 2-second transitions. Most locomotion skills are still correctly modeled, even on those longer sequences. The terrain conditioning becomes necessary in some cases to reduce noticeable feat artifacts, such as floating or terrain traversal. The RTN may fail on cases where the global displacement is small compared to the transition time, or when the desired transition is too far from the training data. Finally, we show results of an RTN applied to temporal super-resolution. In these cases, we apply the network in series to reconstruct an animation saved with only the initial context and a single target state per second. The saved animations were never seen during training and were performed by a novel actor.